Basic quantities that involve magnitudes such as 45 pounds or 60 miles per hour can be represented by real numbers, technically that are called scalars. Okay, so all of those things are technically just scalar terms. Pretty much for your entire existence, you've only worked with scalar terms. Other quantities, called vector quantities, involve both things called magnitude and direction. So we're going to have a magnitude and we're going to have a direction. Typical vector quantities include velocity, acceleration, force. So those of you in physics, you have worked with the idea of vectors. I just don't think we have used vector mathematics to explain them as well as you will see here, because we're really diving into the math of these forces. So for example, if you have the scalar of 50 miles per hour, but you add a direction, east, 50 miles per hour east is a vector quantity because it told me the magnitude, 50, and the direction, east. That is a vector quantity. A vector quantity can be represented with a directed line segment. So in geometry, we would have called these like a ray, but we don't have like a point at the end here and off to one side. It's called a vector, a segment that is directed. This is our vector quantity. Let's highlight that word for us. The length of the vector represents the magnitude of the vector quantity. The direction or angle of the vector indicated by the arrowhead indicates the direction of the vector. So if we see this vector right here is a 10-pound vector 30 degrees above the horizontal. So it gave me the magnitude, the length essentially, 10, and the direction, 30 degrees above the horizontal. So remember, we've done some trigonometry with these concepts. When we did angles of elevation and depression, or all of the navigation we've done in this course, those were mathematical trigonometric functions, but now we're going to put them into vector quantities, which is how most science, and advanced math is done. When we write vectors, we either use boldface type, which is really for a computer, or arrows over the letters, so it will either look like this, bold. I think your homework does this. But our handwriting is not that easy to do that, so we're going to put an arrow above the two letters to represent the vector shown in the figure. When the two letters name a vector, the first letter indicates the initial point, and the second letter indicates the terminal direction or terminal point. Knowing these points gives us the direction of the vector. So if you see the two vectors I have here, vector U or vector capital A, they're different vectors because vector U goes from O to P. It would be called vector OP. And vector A goes from P to O. That's a completely different vector. So the direction it's going is very important for you when you're looking at vectors. They have the same magnitude, but they technically go in opposite directions since the letters are written backwards. The magnitude, to discuss the magnitude of a vector quantity, so if I'm saying OP with the little line over it, I'm talking about the entire vector. But if I want to just talk about the magnitude, or you can think of it as length of the vector, you write it with the absolute value bars. And then I personally will be writing it differently than this. I think this is a typo I never fixed because I can't figure out that symbol. You'll put a little arrow above OP, even when it's inside those absolute value bars, because it's the magnitude, absolute value, magnitude of vector OP. A computer can type boldface. Our handwriting doesn't really have like boldface, so we put the arrow on top of it to indicate that it's a vector. Two vectors are equal if and only if they have the same direction and the same magnitude. So if you see the ones down here, we have a whole bunch of examples. A and B are equal because they're the same length, magnitude, and they go the same direction. C and D are also equal to each other because they go the same direction and they're the same length or the same magnitude. But if we were comparing C to E, do those go the same direction? Are you sure? One looks like steeper than the other, right? So do they go the same direction? So they're not equal vectors. This one is going the same direction as A and B, but is it the same magnitude? No, so it's also not equal to anything else on this page. So they have to be equal in magnitude, and they have to be equal in direction to be equal vectors. Okay, there's a lot of info in this lesson because, again, this is the first time we've seen vector quantities. Got to get a lot of vocabulary out there. Including what it means to do the sum of a vector. When we're working with the sum of two vectors, we are also creating a vector. So the sum of two vectors is a vector. There are two ways to find the sum of the vectors A and B geometrically, which is how we're going to do them, aka we're drawing pictures. You're going to place the initial point of vector B at the terminal point of vector A. So just to make sure we see what's happening here. If I was using vector B, that's this guy. I put the initial point of vector B at the ending or terminal point of vector A. So we have vector A, and wherever A ends, we put B right after it. So the initial and terminal points have to connect. It's purple. The vector with the same initial point as A and terminal point as B is the vector sum A plus B. And to tie this back to why this goes here, just a little preview, what have I created in this image? A triangle. We just learned a bunch of laws of triangles. So vectors, when we add them together, create triangles. We go back to the law of triangles that we just learned. The other way we could do this is to use what's called the parallelogram rule. Ooh, that parallelogram rule wrote that word way too big. Let me try that again. There we go, fit this time. You're going to place vectors A and B. So let's make sure we remember what we're looking for here. So vector A is the purple guy. Vector B is the green guy. And we're going to place them to where their initial points are at the same place. Do you see how I've just basically taken this vector B and like scooted it over so that they both start at the same place? If you look on the outsides and we connected the dots, this would make a parallelogram. Therefore, if you think about it geometrically this way, the diagonal of the parallelogram is this same vector that we had up here making the triangle. So you can think of this either as what I'm calling the triangle method or the parallelogram method. Either way, that's how you do the sum of two vectors. Parallelograms can be used to show that vector B plus A is the same as vector A plus B because vector addition is commutative. You're going to get a new vocabulary word here. The vector sum A plus B is the resultant of vectors A and B. So we're talking about the resultant as what we get when we add these two things together. So the sum is called the resultant. You can think of it like the result when we add them together. I know that I'm talking about the parallelogram rule, and there's a whole lot of things that come with parallelograms that you either slept through or forgot from geometry class. So let's go over them. In a parallelogram, it's called parallelogram because the opposite sides are parallel. So if I was drawing this on here, the parallel symbols are the little arrows. So these two are parallel to each other. And the top and bottom are parallel to each other. That's a rule for parallelograms. We also know that in a parallelogram, opposite sides and opposite angles of a parallelogram are equal. So that means for us, that the sides of here are the same, put the tick marks, and the top and bottom are the same length, put the tick marks. We're also told that the opposite angles, so like this little angle and this little angle, and then the obtuse angle and the obtuse angle on opposite sides of that parallelogram should be the same number. It also says that adjacent angles of a parallelogram are supplementary. Ooh, supplementary. What does that mean they add up to? 180. So this guy should be added together to make 180 with that guy, which then means this guy and this guy add together to make 180. They're adjacent to each other or touching. That works all the way around the parallelogram, by the way. The last thing we know from parallelograms that maybe is not as helpful to us is that the diagonals of a parallelogram bisect each other, but they don't necessarily bisect the angles of the parallelogram. So what that means is that if we have, I'm going to zoom in. Oh, maybe I'm not going to zoom in. There we go. If I have diagonals going from one corner to the other corner on one side, and one corner to the other corner on the other two corners, that those diagonal lines bisect each other. They mean cut it perfectly into two. So like this piece and this piece are the same, and this piece and this piece are the same. Knowing the property of the shapes from geometry class allows us to use a lot of these properties with our parallelogram rule for vectors to answer lots of questions. We have a few more definitions and concepts before we get into a practice problem because, again, vectors are new to us. But going back to vectors and leaving geometry for a second, for every vector, there is a vector, negative v, that has the same magnitude but an opposite direction. So do you see how these go one direction, same length but the opposite direction? Those are called opposite vectors. Acceptable? What's nice, though, is that we have one more vector that's special called a zero vector. The sum of positive and negative vector v have a magnitude of 0, because if we add them together like a positive number and a negative number, they cancel each other out, become 0, right? That same thing happens with vectors, so it's called the zero vector. All of these properties of vectors allow us to use them like they're regular numbers, which is what we need to be able to use our law of sines. The last thing here is that the product of a real number or scalar, some number k, and a vector u is the vector k times u, and has a magnitude of k times the magnitude of u. That is basically telling you that if you take a vector quantity and you double it, the magnitude will double. If you take a vector quantity and you take a half of it, the magnitude will become half of it. So if you see here, this is u. This is 2u. You see how it's doubled? This is 1.5u. See how it's 1.5 times? This is half of u. This is half the size. Did any of those directions change? No, because we multiplied by a scalar number. But when we multiplied by -2, not only did it double in size, what did it do? Flip side. It's now the opposite vector. Notice the arrow came down. That tells us that scalar numbers, the way they've always worked, times 2, times 5, times -3, with regular quantities, also work for vectors. All of this put together will allow us to answer physics questions and speed and velocity questions using the properties of triangles, because those kinds of things have a direction as well as a magnitude. Example 1, we're going to find the magnitude of a resultant. Remember, a resultant is what you get when you add two things together. It says two forces of 15 and 22 newtons act on a point in the plane. Note that a newton is a unit of force that equals 0.225 pounds. If the angle between the forces is 100 degrees, find the magnitude of the resultant force. Okay, first things first, just like with our laws of triangles, we got to draw a picture. So here's my point that's being acted on. Boom. That is my initial point for both vectors. It says that we have two forces. One of the forces is going to be 15 newtons. So here's my 15 Newton force. Pow. 15 newtons. Actually, I didn't want to write that there. I want to call this vector A. At the same time, a 22 newtons force also acts on the plane at an angle of 100 degrees away from the other one. So then it's going to look something like this. Here's vector B. That's 22 newtons. Oops. The angle between them is 100 degrees. I want to know the magnitude of the resultant force. The resultant force, if we use the parallelogram rule, is going to be very easy to find. Okay, wait, I guess, do we understand how I drew this picture? There's a single point where we have two forces acting at the same time. Pow and pow. Like as if you're playing pool, right? And two balls hit a point at once. It has two forces acting on it. We have to figure out where that ball is going.
Wait, but isn't it if it's acting on it, it's going towards it?
As if this is the point and the force is going pow.
Yeah.
And the force is going pow at the same time. So where is this point going if we have some force going that way and some force going that way? Like diagonal, right? That is the resultant vector. We get this by using that parallelogram rule and making a parallelogram out of these two forces. My resultant vector is going to be the vector that I get going the exact direction you pointed with your fingers. This resultant force is the force A plus vector B. Let's back up again. Do we understand the picture now? Better? So we have this parallelogram. Our job is to figure out the magnitude of the resultant force. So our job is technically to find the magnitude of vector A plus vector B. We want to know the length of, for lack of a better word, vector A and vector B. We have this information. We know that vector B is 22 newtons. We also know that vector A is 15 newtons. So question, using the properties of triangles, can I just focus on this part of the triangle? The answer is yes, because if this is 15 and it makes a parallelogram, how much is this? 15. Let's put that 15 down there so it looks right. Using the geometric rules of parallelograms, this angle, like both sides of it, not the cutout side, but this angle and this angle have to add to what? So what is this angle? 80 degrees. If we are looking for this length, this magnitude, you are given side, angle, side. What did we use last class to solve a side, angle, side situation? Law of cosines. The law of cosines, I'm going to write it in regular letters, says that a squared should be equal to b squared plus c squared minus 2bc times the cosine of not b big A. If we rewrite this in terms of what we have on this image, we can use the vector quantities inside the law of cosines to solve for that resultant vector. We would say that the magnitude of A and B squared would be equal to the vector quantity A squared plus the vector quantity B squared minus 2 times the vector quantity A times the vector quantity B times the cosine of what angle? Don't give me a letter, give me a number. What's the included angle here? The included angle? 80. Now to make this more scientifically correct, every single one of these, since we're dealing with magnitudes, needs to have the absolute value bars. Okay. This is, again, literally just the law of cosines, but using the letters from the vector. Do you see how it's the same as this? The angle across from, or the side across from the angle I know, the length of it, so magnitude, is equal to the length of the two sides squared minus 2 times the two sides times the cosine of 80 degrees. Let's fill in what we know here. If we are finding the vector quantity, or the magnitude of the vector a plus b, the resultant, it would be the square root of, what is the magnitude of a? So what is the length of vector a? 15. We're going to square that. Plus the magnitude of vector b, 22. We're going to square that. Minus 2 times those two quantities again, times the cosine of 80 degrees.
Wait, where did the 22 come from?
Where did the, which one?
The 22 of it? Oh.
Oh, that is just, let me go ahead and move it though, because you're right, that is kind of confusing. How about I do this? Is that better? Yeah. I can do this number. Okay. Okay. That's a calculator question. Square root, put all that in there, which we did before. I'm going to fast forward. The magnitude or length of vector a plus b, the resultant vector, is 24.3802 newtons. So you can think of magnitude as length. If we're putting these forces on a piece of paper and describing them as sides of a triangle, it's like the lengths of the triangles, the sides. All of the laws we used before this come along. We also have a method that will find what it is necessary to counterbalance the resultant. That is called the equilibriant. So the equilibriant, I spelled that wrong. Let me try again. Equilibriant. The equilibriant is the vector that is opposite from the resultant vector. And remember, opposite vectors are just positive and negative versions of themselves. So the vector u has an equilibriant that is vector negative u. This is very helpful, especially in physics, if you're trying to combat the forces, like let's say we've put something tilted on a piece, a tilted table, and we want it to stay there. We have to know the friction required to keep it there as the resultant or the equilibriant of that motion, of the forces. Okay. In example 2, we're going to find the magnitude of the equilibriant and then eventually find the angle between the equilibriant and one of the forces. But let's just stay focused first on what we are looking for. First, we're going to find the magnitude of the equilibriant. We have to draw a picture because we have to know what we're dealing with here. So it says there are two forces of 48 newtons and 60 newtons acting on a point A if the angle between the forces is 50 degrees. Okay, let's see if we can do this one. What is the first force? 48. And I'm going to draw it going a particular way this time because I know what's coming. Let's have that 48 be acting on the point and go this direction. So we're going to call this one, we'll just put 48 right here, the vector worth 48. There is another force. What's the other force? 60. So 60 newtons is also acting on it at the same time, but it's going to go like this way. It says the angle between the forces is how much? 50 degrees. We're going to find not necessarily the magnitude of the resultant. We're going to find the magnitude of the equilibriant, which means we need two things. We do need that resultant vector, but more so, we need the magnitude of the opposite vector from that one. But what's nice is that since they are equilibriants, the magnitudes are going to be the same. The direction's going to be opposite, but the magnitude would be the same. Last time, once we had our picture drawn, what did we do to like make a cute triangle for ourselves? The parallelogram rule. So I'm going to close this up with a parallelogram. Your parallelogram doesn't have to be perfect because like this is so not perfect. That's more of a kite actually, but pretend it's a parallelogram. Pretend I'm good at drawing. Okay, we're going to call this point A. We'll call this corner B and we'll call this corner C just because I can see what's going to come here. If that blue part is 48 newtons, then from B to C, because this is a parallelogram, will also be 60 newtons. Again, ignore the fact that this doesn't quite look like a parallelogram. It's not my best. The other thing we know, once we know it's a parallelogram, is that if this corner is 50, what's this corner? How did you get that? Correct. These angles, adjacent angles, are supplementary. So that means this one up here is 130 degrees. Do you see again how we have created a triangle from here to here to here? That is side, angle, side. We can use the law of cosines. Drawing the picture is tough, but it is step one in all of these. If you've taken physics before, I'm assuming that was always step one in the forces unit, so you could see where it was going. So if we write this down, here, let's label some more stuff. We're going to call this vector V, so that this is the negative V, so that we know what we're searching for. The law of cosine says that the opposite side's magnitude squared would be equal to the two side lengths squared, so this is going to be AB squared, plus BC squared, minus 2 times the vector magnitude for AB times the vector magnitude for BC times the cosine of the angle between them. What is that angle between them?
Wait, what was the question?
What is the angle I should put right here? 130, because this is one side and this is the other. We want the angle between them. If you wanted to use letters, you could call that angle B since we named it B, or angle ABC since we gave 3 things 3 letters. Once we have this point, we're just throwing things into this formula. The magnitude of V, which would be the same as the magnitude of the resultant, will be the square root of the magnitude of AB, which is 48, plus the magnitude of BC, which is 60, minus 2 times the magnitude of AB times the magnitude of BC times the cosine of 130 degrees. We throw that all in a calculator, we make sure it's in degree mode, and we find that the magnitude of vector V, that resultant vector, would be 98.0125 newtons. But remember, that's this vector. We were asked for the magnitude of the equilibriant, which is the opposite. What is the magnitude of the opposite if the resultant is this much? It would be like the same. So the magnitude of the equilibriant, aka the opposite, would literally be the same because the magnitude is the same. The only thing that changes is the directions. And next class we'll figure out the direction of this angle. Now that we're back and we're finding this angle, we are really looking for this angle right here. We're going to call that angle alpha. Interesting. Here's some things I notice about this image, and this is why drawing a picture is very important. If you look at the pink line and then the resultant vector that I've drawn with a black line, they make a straight line, yes? Straight lines have to add up to how many degrees? 180. So theoretically, what could I do to figure out what this is? Subtract another angle. Do I know this angle that I want to subtract yet? No. So here's what we're going to write down to show ourselves some steps. We're going to say that we would find the measure of angle alpha. This is the same example we stopped on because we were not finished. This is why we should not be on our phones. That's an alpha. Bless you. Alpha is going to be equal to 180 degrees minus some angle, but we need to know what this angle is. Right now we have no symbol representing this angle, and we can't call it angle A because that's this whole thing, 50 degrees. So how else, think back to geometry, could I name just this little part right here? Maybe make my arrow go bigger, give you a hint. Angle CAB, starting at C, vertex at A, ending at B. That tells me how that angle works. So we are saying that we could do 180 minus the measure of angle CAB, which means we need to figure out the measure of angle CAB. We're going to have to come to a sidebar to do that. Let's think what we know about that particular angle. Don't color yours in because you're going to get mad because I'm going to erase mine in a second. But if I was trying to find this right here, compared to this triangle that I already know, what do we have that we can use to solve for that missing angle that we maybe learned in section 7.1?
We have two sides.
We actually have more than that. We do have two sides in an angle, but what did we just find in the part of this problem before? We also have the vector v. That's the resultant vector. In which case, what do we have here? A pair. You have the angle and you have the side across from it. When you have a pair, a side and an angle, what law can you use to solve? The law of sines. So the notation down here is going to take us a second to write down because it's not just A, B's, and C's anymore. We're going to have to be specific. We can say that the sine of angle ABC over the vector V should be equal to the sine of angle CAB over the magnitude of vector BC. Now let me make sure we understand what I'm writing down here. When I use the magnitude of vector B, what is the name of this angle? Give me three letters. ABC. That's why I used ABC. That's my pair. And then for CAB, what's across from CAB? What two letters? BC. So we're using geometry terms and geometry formulas because we have way too many letters floating around here. We need to know exactly which angle and which side we're talking about. But once we do this, we have three of the four missing pieces here. What angle is sitting there in ABC's angle? Look at your triangle. 130. So this is 130 degrees. And we just found that the magnitude of vector V is 98.0125. That's going to be equal to the sine of CAB over the magnitude of BC. What is the magnitude of BC, of that side length? 60. We are setting up a law of sines. It's only confusing because our picture has a lot going on in it. But you guys were great at doing this particular step. After this, we cross multiply and divide. So this would be 98.0125 times the sine of CAB equal to 60 times the sine of 130 degrees. What do I divide by on both sides? Yeah, so it'll be 60 sine of 130 degrees divided by 98.0125. Can I throw that in a calculator right now?
No,
We have to do the inverse sine. Since we're looking for the angle is inside of sine, so angle CAB will be equal to the inverse sine of all of that. When you compute that in your calculator, in degree mode, I'll pause. Let's see what we get. Should get 27.9659 degrees. So boom, we have angle CAB. So we can go back to the idea of supplementary angles here and find that angle alpha is equal to 180 minus that 27.9659 degrees. So we end up finding out that angle alpha is 152.0341 degrees. Vectors will be easier if you can draw good pictures. The same way on the other one when we had the point that had two vectors going off of it and we made a parallelogram, same thing here. But bottom line is you get to use your laws of triangles that we did in the previous chapters. So if something is wrong and you can't use one of the laws, your picture might be wrong. We can also use vectors to solve problems on an incline. So those of you who have taken physics, you've probably seen, I think they're called dot diagrams, where you have like a dot and then arrows going certain directions to represent forces. This is the math that goes with that. We're going to try to find the force required to keep a 50-pound wagon from sliding down a ramp that has been inclined at 20 degrees to the horizontal and assume there's no friction. So we're going to have to hold it up there somehow, and we want to know what force is required to hold it up there. We see in this image that this angle right here is 20 degrees. I'm giving you a hint here. Where else does it say 20 degrees? If they give you the angle of incline, that means they've given you the angle down, straight down, not straight down, but straight down from the ramp, perpendicular to the ramp, if you will. Okay? The other thing it says is that this wagon is 50 pounds. Those of you who have taken physics, you know that weight always goes straight down. So look at this vector representing the weight, starting here and going down, because that is a force that goes downwards. Here's what we need to know. We need to know the force that we'd have to use to keep this up here, which means we're looking for the magnitude of AC. Okay, this picture has been provided for you. What do you notice about this cute little triangle that's in here?
Isn't it that angle 90 is 20? So the other angle would be 70.
Absolutely. We have a lot of information here because one of them is 90 degrees. So here's what I want you to do, because I know yours also prints kind of dark. We're going to draw this triangle again for ourselves just over here so we have it. And we have all of the numbers showing. So this is going to be A, this will be C, this will be B, and they did label it for us. That's super nice. Angle ACB, or angle C, since this doesn't have a ton of letters floating around, is 90 degrees. You guys told me that since this is 20 degrees, that angle A would be what?
70.
Amazing. Fabulous. Awesome. The other thing I notice is that because this is a 90-degree angle, all of the trigonometry we learned from the very beginning of this class with a right triangle, you can also use. If you love the laws of sines and cosines, go for it. But since this is a 90-degree angle, you can go back to using the original trig you learned, which was SOHCAHTOA. Sine is opposite over adjacent, cosine is adjacent over, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. Throwback. Anytime you have a 90-degree angle, you can go back to these. So let's look here. We are trying to find the friction it takes to keep, not friction, the force that it takes to keep this up. So we are looking for the magnitude of AC. The only other number that we have here that I forgot to label on my triangle is that 50-pound weight. Do I put that 50 pound between B and C or between B and A? B and A. Okay, cool. So that means that we have the hypotenuse. When we are looking for AC, we can use any of the trig we've learned before. Specifically, here's how I'm going to do it this time. This is going to be the sine of big B. Sine is opposite over hypotenuse. So what angle, or sorry, what side is opposite of B? AC. Do you see why I picked sine? Hypotenuse. It's the 50. I'm going to write it right now as the magnitude of AB so you know where I'm getting these numbers from. The sine of angle B will be the magnitude of AC divided by the magnitude of AB. Wow, I didn't even write these correctly. They should have the little symbol above them. So let's fill in what we know. We know that big B is 20 degrees. We don't know the magnitude of AC, that's what we're literally looking for. But the magnitude of AB, you guys told me, is 50. How do you solve this? Multiply by 50 on both sides. So the magnitude of vector AC will be equal to 50 times sine of 20 degrees. This is literally the law of sines, just simplified down. So what is 50 times the sine of 20 degrees?
17.0110.
So the magnitude of AC, or the force required, is 17.1010 pounds. After lunch, we'll pick this right back up. A force of 16 pounds is required to hold a 40-pound lawnmower on an incline. What angle does the incline make with the horizontal? So again, we have a point B where this, a lawnmower is putting force of its weight straight down to the earth. And then you have the force from the ramp that also creates this vector BC. We are told that the force that it is used to hold it up is 16 pounds. So now this time we were given vector AC. The question is, what is this angle? But easier, and if we remember what happened last time, where else did I put this 20 degree? Where B is. So if I'm looking for this angle theta, where else am I looking for theta?
B.
Angle B. So let's draw our little triangle over here so we can really see what's happening. We have, not with that color. Boom, boom, boom. We have our 90-degree angle. This is A, this is C, this is B. You guys told me theta is on angle B. Vector AB has a magnitude of 40 pounds. Vector AC has a magnitude of 16 pounds. And so again, because we have a right angle, we can go back to regular sine, cosine, and tangent instead of having to use the law of triangles. But the law of triangles also works because you have a pair of big C and side length AB. You can find this missing angle B. Or we can set up old-fashioned trig. Again, because we have a right angle, we can use SOHCAHTOA to do this. If we want angle B, what two sides do we know compared to angle B? Do we know the opposite, the adjacent, or the hypotenuse? We know the opposite and hypotenuse. So again, we're going to end up doing sine of angle B will be equal to the magnitude of vector C, that's opposite, divided by the magnitude of vector AB. Now this time, remember, we are looking for this angle B. We're looking for theta. So we can plug in what we know. We know that sine of theta would be equal to the magnitude of AC, which is 16, divided by the magnitude of AB, which is 40. And then since I'm looking for the angle, do I just type that in my calculator? No, what do I do? Inverse sine, because we want to get theta by itself. So this will be sine inverse of 16 over 40. That's a calculator question. So hey, calculator, what is the inverse sine of 16 over 40? Thank you, 23.5782 degrees. So sometimes these vector questions are the, quote, easy trig, and it's only easy because you've been doing it longer. But again, you can use the law of triangles to do these questions since it's a 90-degree angle. If it wasn't 90 degrees, you'd have to go back to the laws of triangles that we had before. Our last question is a navigation question. This is where vectors really come in handy because they show direction. So it says, a ship leaves a port, here's the port, on a bearing of 28 degrees. So look, it's headed this direction, 28 degrees from north, and it travels 8.20 miles. So the magnitude of vector PA is 8.2. The ship then turns due east, pow, and travels 4.3 miles. So the magnitude of vector AE is 4.3. The question is, how far is the ship from port? So we want to know the magnitude of this side of vector PE. We then are going to find its bearing from port. We'll get there later. So we are going to find a magnitude, and then we're eventually going to find a direction. So the first things first, we're going to find this resultant. Remember, the resultant, that's not how you spell that. The resultant is going to be vector PE because we are looking to add vector PA to vector AE. That's the resultant. Since we are looking for what is essentially the long side or one of the sides of this triangle that we've created, and we know a side, we know an angle, and we know a side, we can use the law of cosines to do this. The law of cosines with the letters from today's problem will be the magnitude of vector PE squared will be equal to the magnitude of vector PA squared plus the magnitude of vector AE squared minus 2 times the magnitude of vector PA times the magnitude of vector AE. Get that right. Multiplied by, I ran out of space, the cosine of angle PAE. Okay, very confusing with all of these magnitudes and squareds and arrows floating around. I get it. It is just the law of cosines. And remember, the equals side is the one we're generally looking for. So we can square root everything to find the magnitude of PE. And let's go ahead and plug in some numbers for ourselves. What is the magnitude of vector PA? 8.2. So that's going to be 8.2 squared. Plus the magnitude of vector AE. What's the magnitude there? I don't know, I put that extra 0 there. Minus 2 times the magnitude of vector PA, which you guys told me was 8.2, times the magnitude of vector AE, 4.3, multiplied by the cosine of angle that is included in between them. What is the degree measure of that angle? 118 degrees. It's law of cosines with crazy symbols for all of the vectors and their magnitudes. Is there anything left here that I need to solve? No, so we can throw that into a calculator. And in one fell swoop, you can find me what the magnitude of PE is? What is the magnitude of PE? 10.9012 square, or miles. I don't know why I said square. Fabulous. So now we know the distance of the ship from the port. We know the magnitude of that vector. The second question is asking you to find the bearing from port, meaning we want to know the following angle. We want to know how many degrees it takes to go from north to vector PE. Without using fancy vocabulary, looking at this image, what one thing do we need to find to be able to know this entire direction, this entire angle, alpha? Be more specific, please. Because P looks like it could be multiple angles right now. What specifically? EPA. We need to find the angle E to P to A. Because we already know the angle from north to P to A is 28 degrees. So if we find this one, we can just add them together. Easy peasy. So if we're finding alpha, which is our bearing, we said it would be nice to do 28 degrees that we already know plus angle EPA. So we need to take a second. We need to figure out what angle EPA is. Sidebar. Now, this is very similar to the other question we did like this with that resultant vector. Angle EPA can be found using the law of sines because why? What law, I guess is my question. What law can we use to find this angle? What do we know the pair of? Huh? No, what two things do we know that become a pair? Be more specific.
PE and A.
We know the magnitude of PE, and we know this angle A, which means we have the angle and the side across from it. That's a pair. So we can use the law of sines to find the missing angle that we want. We will be doing, and I wrote too far to the side, so I'm going to move my arrow just a little bit so I'm not off the page. We're going to do sine of angle EPA over its missing side. What side? Give me letters. What side is across from EPA? AE. So that will be the magnitude of vector AE. That'll be equal to the pair that we know. We know angle, I'm going to use 3 letters here. I know it's angle A to most of you guys, but since we did 3 letters in the first one, we're going to do 3 letters in the second one. Over the magnitude that we just found, PE. So again, we don't know angle EPA, so we're going to leave that as the letters. The magnitude of side length AE of vector AE is 4.3. Angle PAE, that was the 118 degrees. And we just found that this vector, magnitude of the vector PE, is 10.9012. We cross multiply. 4.3 times the sine of 118 degrees equal to 10.9012 times the sine of EPA. We're dividing by nope, not wrong side. We're dividing by 10.9. I'm writing all the wrong numbers. Dividing by 10.9012. That's going to be equal to the sine of EPA. Can I throw that in a calculator yet?
No.
What do I have to do on both sides? So the angle EPA will be equal to the inverse sine of all of this. So the measure of EPA is 20.3822 degrees. So we can take it back. Now that we know that little angle, we can add it to the 28 degrees we already knew from the question to find alpha. So my alpha will now be 28 degrees plus 20.3822 degrees. So we learned that alpha is equal to 48.3822 degrees. And that is the bearing, again, the direction the boat technically has traveled from port if you were a bird and could fly straight there. The bearing from port.